the future of aircraft propulsion, and it's being led by the Associate Administrator of Aeronautics Research Mission Directorate, Mr. Bob Pearce.
Okay, good afternoon. It's my pleasure to be moderating this panel on the future of aircraft propulsion. I've got 4 distinguished panel members that I'll be introducing. The way I'll run it is I'll introduce each of them now, and I'll provide a few words of opening comments, and then I'll turn it over to the speakers, and each one will speak in turn. And I'll introduce them in the order in which they'll be speaking. So the first panelist will be Jimmy Kenyon. He's our program director at NASA for ARMD's Advanced Air Vehicles program, where he leads all of NASA's research efforts in airframe and propulsion systems. He's also been an executive at Pratt & Whitney and had leadership roles in DoD as well in the past. The second speaker will be Arjun Hegemon. He is the general manager for GE's GE Aviation's Advanced Technology Organization, where he's got 22 years of experience in advanced technology and new product introduction, including leading development of the LEAP-1B product line. The next speaker will be Frank Preli. He's VP of Propulsion and Materials Technologies at Pratt & Whitney, and he's got over 40 years of experience at UTC leading development of technology for aerospace and energy, for the energy markets. And finally, Tim McCartney of NASA. He's the Director of Aeronautics at the Glenn Research Center. Obviously, the Glenn is where we do our propulsion research. He's also served as the Chief of Advanced Aircraft Project Office at Glenn and has served a number of other senior roles at Glenn over the last couple decades. So those will be our distinguished speakers. We'll get into the details of the subject of the panel. But before we start that, I just wanted to provide a few opening comments. So first, I just wanted to say that we recognize the extremely challenging environment we are in today. With the COVID-19 pandemic, it has led to an enormous ongoing contraction of the aviation market, which is having major impacts on airlines, OEMs, and the supply chain. But even with that, we see that we are on the cusp of game-changing innovation that will transform aviation and mobility. We're about 50 years into the modern aviation era. If you think back, and between about 1958 and 1970 or so, we saw in the U.S. we saw the introduction of the 707, 727, 737, 747, DC-8, 9, 10, and L-1011. So, those were all on a set of technologies, jet engines, which is obviously apropos to the subject of this panel. But also swept wings, area ruling, supercritical airfoils, all of those were introduced in that period, and it really did create this modern aviation era. And what I want here to say is that, we are on the cusp of inventing the next 50 years. We are inventing the next 50 years right now. So some examples, UAS, drones will be serving a broad range of needs, from package delivery to aerial photography to infrastructure inspection. It's going to provide benefits to every person as we look out to the future. Advanced air mobility systems will emerge based on innovation in electric vertical takeoff and landing aircraft. They're going to serve to create new markets, new mobility networks in urban and regional markets, bring a third dimension in transportation to the local market. Next, traditional aviation, which is most familiar to most of the American public. The airlines that fly us all around the U.S. and all around the world will also see a revolution as technology such as the transonic thrust brace wing and hybrid electron propulsion technology rapidly advance and become available for product introduction in the next 10 years or so. And for global connectivity, speed matters. If you think about the distances that we fly today, when we fly from the US to Asia to Europe and so forth, and we fly those more often, speed does matter. So supersonic commercial transportation is I think just around the corner, with early innovators developing products today. And of course, NASA's work on low boom technology that will enable further advancement and enable overland supersonic transportation. And then if we look further out, hypersonics could also be the ultimate in point-to-point transportation with speeds that will connect very long global ranges in less than so you could do less than days travel or days travel to the far reaches from where you are today. So a tremendous amount of innovation is on the drawing boards today, and propulsion is the key to all of those innovations, right? Without innovation in propulsion, we're not going to go anywhere new. So that's what we're going to talk. We're going to talk about two of those key areas where there's really some exciting innovation. So the first is in electrified aircraft propulsion and hybrid electric propulsion. Of course, that is being fielded today in UAS, which are all electric, and of course, electric vertical takeoff and landing is right on the horizon. That products are being developed and are starting to go into certification. And then hybrid electric propulsion for large transport is in the lab today, and we're ready to get to flight. And of course, hypersonics would be the other extreme as we look at the ultimate challenge in speed and the challenge of technology to provide the kind of propulsion that would allow us to travel at high Mach number, Mach 4, Mach 5, and so forth. So with that, our panelists will talk about some of the things going on in those two areas. I think provide some really good insights as to the timeframes and performance and technology challenges we see as we enter into this new era of innovation. So with that, let me turn it over to Jimmy Kenyon to kick things off.
Great, thanks, Bob. Appreciate the introduction. Really happy to be here. Really happy to talk to you about the future of aircraft propulsion, and kind of frame the discussion. I want to look at it in sort of two sets. First off is kind of what's next. What are those things that while right around the corner may be an overstatement, but they're really going to be the things like Bob just referred to that kind of drive the next 50 years of commercial aviation and moving people and goods around. But then beyond what's next, what's on the horizon. And so if we'll go to the next chart, please. What's next? Well, we're not going to start over. We're going to start with the gas turbines we have because they are really very efficient. They're really effective for their size and their weight, but they've got a long way to go in terms of what they can provide. And so we're going to keep working those, but where we're going is looking at driving the thermal efficiency of those engines and looking at smaller and smaller cores. And by driving those small thermally efficient cores, what that enables us to do, of course, is go to higher bypass ratios, potentially without increasing the size of the engine. That's a great benefit. But it also gives you some great advantages in terms of just power density and energy density that you can use to drive innovation across a lot of things, including better integration with electric cycles for hybridization and whatnot. So right now, what we're going to see at NASA over the next several years is a huge focus on driving towards small and thermally efficient cores and dealing with some of the key challenges in terms of things like tip flows and leakage flows, the materials you need to push the pressure ratios and temperatures up on those while enabling them to stay very small and very compact. Beyond that, there's still plenty more to do in propulsors as well. We've made tremendous progress over the last number of years, the so-called ultra-high bypass ratio engines and the fans associated with that, continuing to push those bypass ratios, but what you're really pushing is the fan pressure ratio, because that's where you get your efficiency, and then how that enables you also to optimize the rest of the cycle. And so a lot of work on the higher efficiency engines is sort of the baseline, but then we go to electrification. And electrification is really a game changer here. So why electrification and not electric? Well, when you look at the larger engines, what we're really looking at is more along the lines of hybrid cycles. Looking at how we can increase the amount of electrical power we're getting, how we can better integrate that with the gas turbine cycle. And by doing that, you can optimize your engine and your propulsion system differently, which can allow you to do things like size your engine to be more effective for the mission. It can allow you greater power offtake to drive the increasing number of electrical systems all around the airplane. And so a lot you can do with hybrid cycles for smaller aircraft like single aisle applications. But we also have electrification on the lower end. And of course, We are flying all electric on our small unmanned aircraft, our small drones and whatnot. Those are electric, those are battery powered. But as we start to scale these up, electric propulsion becomes an enabler for the so-called eVTOL market, the electric vertical takeoff and landing market for applications like urban or advanced air mobility. And when you start carrying high-value goods and maybe even people on these, now it becomes all about safety and reliability. And that's where we're focused. Understanding these electric components, when you put these electric components together into a propulsion system, and you put them into a flight environment, how reliable are they? And that reliability, the fault management, the fault tolerance is how you drive safety with those systems, because obviously the reliability and losing an electric system is not a good thing when you're flying people and goods around. And so working on the safety and reliability of these propulsion systems, understanding what are the key drivers to reliability, and then attacking them with advanced technology to make that reliability better and better. Now, when you put all of that together, looking out a little bit further, then you can start thinking about how you might use these small core engines with the advanced propulsors and the more electric architectures and enable increasingly innovative, novel propulsion and airframe integration. Things like distributed architectures or more distributed architectures, as well as maybe even boundary layer ingestion. And we've worked on some of that before, but as we start to mature these propulsion systems, that becomes a key enabler for allowing us to do this and optimize better at the system level. So that's kind of what's next, but then what's on the horizon? If you don't mind, let's go to the next chart. What's on the horizon, I think, is going to be all about speed. How do we go faster? How do we connect people faster? How do we give people more of that precious commodity we can never get more of, which is time? How do we give that back? And so supersonic flight, of course, is a key enabler. And as Bob mentioned, we're focused on low boom flight demonstrator and figuring out ways to mitigate the effects of the boom that would enable overland supersonic flight. But from a propulsion standpoint, once we start to get our eyes on that problem, we've got to start thinking about the propulsion system, because we've got to overcome some key barriers there to really enable this market. One is cruise efficiency. We don't want to do that afterburning. And so we've got to get after ways that we can keep that higher thrust up, higher pressure ratio fans and get really good cruise efficiency for the long haul with these supersonic engines. The other part of that is dealing with noise. Of course, higher pressure ratio fans are going to increase the noise on the ground, and landing and takeoff noise becomes a key barrier. Of course, there's going to be en route noise as well, and so we've got to understand and work those issues as well. So propulsion is going to be a key driver, and of course, sustainability when we start flying these things at greater and greater scale. Beyond supersonics, though, the speeds keep going up. People want more time back. And hypersonics becomes a really interesting future market. And we're starting to see some commercial interest in the potential for a hypersonic commercial point-to-point market. From a propulsion standpoint, though, there are some really key challenges there. And probably number one on the list is reusability. Of course, any sort of a commercial airline, you got to fly there, you've got to turn around on the ground, and you got to get back. Well, your propulsion system has to be reusable to do that. And it has to cover a wide Mach range from takeoff all the way up to cruise and then back to landing. So you look at things like combined cycles, so-called turbine-based combined cycle, but various kinds of combined cycle engines, or maybe even some novel cycles and architectures. And there are several ideas out there that are really interesting and innovative. And of course, when you look at that, a big part of reusability is also going to be durability, which means higher temperature materials, better cooling technologies. So a lot of difficult challenges out there, but things that are really going to drive innovation. And as we deal with all of these sorts of things, by the way, all of these capabilities, all of this innovation comes back into our propulsion systems like we see them today and enable even greater advancements. So what's next? What's on the horizon? Really exciting, and it's all driven by propulsion. And so with that, I appreciate your time, and I'll pass it over to my next colleague, next panelist, Arjun Hegemon. Arjun, over to you.
Thank you, Jimmy. Thanks everyone for making me part of this discussion here. I look forward to it, proud to be here. Jimmy, you gave a great summary of, what's ahead in the future of propulsion here. I put a couple pages together from a GE perspective on where we're focused. We're focused both on sustainability and engine efficiencies, engine performance, as well as the supersonic application. For the forum here, I chose to kind of look at, you know, what are we doing, what's ahead of us in the future for sustainability and reducing the emissions by increasing the efficiencies of our future engines. Unfortunately, I can't seem to see the pages, so let's go to the first page, which is called a significant commercial portfolio refresh. So we just came out of a period of over the last decade of a massive overhaul of all our commercial products. The CF6 was replaced by the GE9X. The GE90 is currently getting replaced by the GE9X. The LEAP engine, which I was part of, is replacing the CFM line, and then we're adding the catalyst to our portfolio. All these engines achieved effectively a 10, 15, 16% efficiency improvement over its prior generation. And Jimmy, as you referenced it, that was all achieved by basically going after propulsive efficiencies, and a lot of it was all in thermal efficiencies, using new materials, new technologies, and a large part of it as well was new capabilities of our analytical tools and truly understanding, you know, how to improve our airfoil designs, how to improve the flow path, how to improve all our cooling streams, cooling flows, and whatnot. So that's what we did in the past. The next page basically describes what we're doing in maturing our technology. So we have a commercial portfolio, we have a military portfolio. We also have demonstration engines portfolio. Every so often, you know, when we have developed enough maturity in various technologies that are not currently within existing engines, we will end up building a demonstrator engine that starts combining all of those together such that we can truly look at the overall system and the integration of all those different technologies. Whether it's at the system level, the component level, the controls level, all of it gets brought together. And it gives us unique insights to truly understand the overall system integration of the engine, and ideally have it on a test bed where we can fly it at altitude and get those learnings. So we have an extensive history here, and you know, I'm pleased to tell you that we're very much gearing up towards our next demonstrator engine, which will have a lot of the things in it that Jimmy, you talked about. It will have a high-tech compact core with a lot of new technologies that unfortunately I can't really divulge here in this forum. But it deals with the small components. It has the new material with higher temperature capabilities. It has the advanced cooling, that we can get the same surface temperatures while using less cooling flows. So we really think we'll get to that next level of thermal efficiency. In addition to that, we're going after the propulsive efficiency through some revolutionary architecture updates. And then with all that, a truly new technology that goes in there. Jimmy, you covered it. It's our hybrid efforts. We'll start building hybrid propulsive engines that I'm convinced are the future. It's just a matter of how much power do you extract out of it in a next generation versus multiple generations down the road. And I think multiple generations down the road, when the airframers really start utilizing it for distributed propulsion and the different aircraft systems, I think that's really where you get to that level of entitlement. So I talked a little bit about the past, the recent engine overhauls that we have done. I talked about this maturation effort, the way we run through it and start putting it into demonstrator engines. Kind of want to extrapolate it forward a little bit. So on the next page, the 2013 Dayton Epicenter. So the next couple of pages, we'll go a little bit through, you know, what we have achieved to date in our hybrid efforts. Those are real accomplishments, and it sets us up well for the continuing maturation that in our next demonstrator engine, we truly have that as a working system. So it starts in, we really started getting seriously engaged on the hybrid efforts in 2012. In 2013, we built our facility where we're really running our hybrid efforts out of. It's a facility where we can test up to 6 full aircraft electrical systems simultaneously, so there's plenty of available power. It's got all the supporting electrical infrastructure, and that's really our center of gravity in all our hybrid efforts. On the next page, we go to 2016. That's really the first big test effort that we did in partnership with NASA. It was the F-110 dual spool engine demo, where we had a 1 megawatt power extraction simulated at altitude in the altitude test cell at 51,000 feet. It was an industry first, and it gave us a lot of insights and learnings on how to move forward. On the next page, 2016, really 2017, when it finished, we built our first electric motor generator. You can see it's not really packaged for flight, but it was a turboprop thrust class effort where we have a turbo engine with a generator and really are able to run it. And again, a 1 megawatt power extraction on a somewhat smaller engine than the F-110 we ran previously. So this was a ground demonstrator that we did. Then on the last page here, showing the NASA NEAT facility in Sandusky, Ohio. Again, a joint effort within that partnership where, it's one thing, you've got the motor, you got the turbo motor, you got the motor generator, the electric motor generator. There's a whole control system that goes with it. There's one thing of testing it all at ground level. When you start bringing all that at the high power and high voltage that we're running for our thrust class applications, running it out at altitude becomes a lot different. And there are a lot of new learnings there that we're discovering within this facility. So here's where we're putting everything together, testing it at altitude, not just the motor generator, but the overall control system, and ultimately the battery system as well. And we should make a lot of progress on that this year and next year on our way towards actually flying it in a demonstrator. Again, I wish I could share more about the details and all the things that we're doing there, working towards that. But for now, all I can tell you is to stay tuned. It's a very exciting future that we have here. So with that said, I'm proud to hand it over to my colleague, Frank.
Thanks very much. I'm Frank Preli from Pratt Whitney. Thank you very much for tuning in today. And also, thanks for inviting me to participate in the panel. If we move to slide 2, talk a little bit about our business. What we're all after is a sustainable aviation business. And many of us think when we hear the word sustainable aviation, we think of the environment, which of course is a hugely important part of this, but it's in terms of the business, it's also making sure that you have mobility demand, that people want to go somewhere. And we took for granted that this is a very strong and growing demand, but I think this year we found out just how fragile this can be with capacities down by 90–95% due to the COVID crisis. So this is something that must be paid attention to. Oil price and availability has not been a big issue for the last 10 years or so, but in the past it has been. The environment, I'm going to talk a little bit more about that. And then, of course, customer value. Are the customers of our products, the airlines, are they able to extract value? And if you've been reading the news, and I'm sure everyone has, the airlines are really, really struggling, really not able to continue without some form of assistance. So as we look at sustainability, we look at trying to improve efficiency, reduce the environmental impact. And so on the next page, slide 3, on the left-hand side, we take a look at, if you want to improve efficiency, what should you focus on? And so this is where emissions come from, and this is where fuel is consumed. It's largely twin aisles, long-haul aircraft, and also single aisles. If you add up the business jets and the regionals and the turboprops, you're less than 10% of the total environmental impact, less than 10% of the fuel consumption. So, from our point of view, the place to focus focus is single aisle and twin aisle, although the technology level as it exists today sort of pushes you towards the smaller things. But in the end, smaller improvements in efficiency to the single aisle and twin aisle will have a far greater impact than will big improvements in the smaller segments. Over on the right-hand side, we take a look at what is the problem if you want to fly this. First, you know, if you look at automobiles, you see they don't require a lot of power and they don't have to store a lot of power on board for it to take a trip. If you move on up though on the yellow dots through the airframes and aircraft, you can see that once you get to single aisles like the 737 and the Airbus 380 twin aisle, you're talking about huge amounts of power requirements and staggering, really staggering amounts of onboard energy that you need to carry out, particularly a long haul flight. So our issue as we move towards higher efficiency, and in particular, as we look at electrification is, you know, how can we get a lot of power and how can we store a lot of energy on board? And both Jimmy and Arjun, you know, kind of referred to, you're not going to do this all with batteries in the twin and single aisle until batteries are hundreds of times better than they are today. So what can you do? If you go to the next slide 4, you know, we've seen a lot about using electrification, all electric for personal use and taxi use. And of course, this makes a lot of sense. If you remember the previous chart I showed, you don't need to store a lot of energy on board and you don't need a lot of energy to make these go. Our focus has really been more in the regional and large, where more than likely a hybrid electric approach is going to be the way to go. You simply can't store enough batteries on the aircraft, nor do you maybe want to, because if you can size your turbofan for optimum performance at cruise, you will have a very highly efficient, low emissions system. You can use the batteries as takeoff assist and to minimize the designs that you have to do to look at the endpoints and the outer regions of the flight envelope. So, you know, an awful lot of the mass of the engine today is for single engine aborted takeoff go around. And so if you were able to use electric hybrid to help out with that, you'll be able to use a much smaller core, even a smaller fan. And so that seems to make more sense for the near term. So if we go to the next chart, I'll just wrap things up talking about, you know, evolutionary wise, as a business, as an industry, we've been making approximately 1.5% improvements in efficiency continually since the dawn of the jet age. The next thing, as I alluded to earlier, is moving to smaller cores, smaller, higher efficiency cores, coupled with electrification, which will give you a much better efficiency level than we have today. And then sustainable aviation fuels. These I call evolutionary because you're using this basically the same architecture of the turbofan as we use today. We're doing maybe high and low extraction of power and power assist. Sustainable aviation fuels, most engines are relatively easily adapted to run on these. Some don't need any adaptation at all. And then if we look towards the future beyond that, revolutionary, we may be looking at different kinds of airframes and aircraft with boundary layer ingestion. I think Jimmy mentioned this. We're also looking at some pretty radical changes to the use of the gas generator in terms of using bottoming cycles, recovery cycles, using the gas turbofan, or actually would just be a gas generator, as an electrical generation device rather than a propulsion device. But these cycles still have a ways to go in terms of technology development. And then maybe finally looking at things like hydrogen. It's a in terms of storage and the amount of energy you have to have on board, it's a tall order, but it does promise one day to get closer to zero emissions. So with that, I think I'll pass it over to Tim McCartney, and he will be our final speaker.
Thank you, Frank. Appreciate it. Appreciate the opportunity to talk with this august group here, and don't want to forget to thank the American Astronautical Society for putting this together for us. As I bring it home here, I'm going to try and bring a little bit of the local flavor, really what Glenn is doing, NASA Glenn in Cleveland is doing to kind of achieve that vision, ARMD's vision as we work on Jimmy Kenyon's program. How we do that in partnership with industry. If we can go to the next chart. So first, I wanted to just quick rundown for those who may not be familiar with what Glenn does, and the kind of technologies that we are deeply involved in and spending a lot of time working on. It's not a complete list, but certainly what is commanding a lot of our time these days. Glenn is a propulsion center. It's at its core capabilities, it's air breathing and in-space propulsion, power systems, aerospace communications, and materials for extreme environments are our core competencies. So some of those, and I'll run down this, and we'll talk more about the electrified aircraft and some of the technologies that we're working on to achieve what many of the panel members have been talking about. It's a big push at Glenn. We've converted many facilities. We've hired, we've staffed up to meet this challenge, and are determined to knock down barriers to achieve those goals. We talked a little bit about the high power density core, thermally efficient core. We're getting ready to kick off a new project to look at that and continue the work that we have been doing. Not only increases, the smaller core, not only increases the turbofan efficiency, but it's a real enabler for electrified aircraft. We talked about, power extraction you heard about today. Getting greater efficiencies will certainly help in that regard. Today, Glenn is working in partnership with GE and Pratt to tackle these problems in a couple of the facilities and some of the research programs that we're working. On the urban air mobility front, Glenn has a significant role in the aero communications that are going on. Working hard with the program to help design the next generation of safe, secure air traffic management systems. Not so much the management systems, but doing it safely and securely in the communications piece of it. On supersonics and hypersonics, Bob mentioned about the need for speed. Jimmy mentioned getting that commodity back. That time, Glenn has a long history of working high-speed propulsion systems with supersonics and hypersonics, and numerous test facilities where we are running full-scale engines at altitude, as well as components, inlets, nozzles, and propulsion systems in the test cells. Today, we have hypersonics work going in the 10x10 supersonic wind tunnel, in our propulsion systems laboratory, in many of the SEALS labs that we're working in. And we have a test coming up in the 8x6 transonic wind tunnel to support the low boom flight tests that are coming up. On propulsion acoustics, again, a long history of modeling and of testing. I don't think any of us fly today without some technology out of NASA to help reduce that noise on the aircraft. And we'll continue to do that as we move into the supersonics. Icing, although it is as big a pull, we still have the foremost experts around the world coming to IRT, our icing research tunnel, and working with the icing experts at Glenn. I'll mention a recent capability in our propulsion systems lab. we added a new capability to add an icing to investigate a recently kind of unknown phenomena where we're icing accreting inside the engine of a low pressure compressor. The data that we've taken, the modeling we've done will help assist in future designs as well. So enough about Glenn overall. We'll jump into the next chart. Assuming it has come up. So we heard a lot about the advantages of electrified propulsion and kind of talk about the architectures, and certainly we're doing a lot of that work. It's a lot more than just electrically powered airplanes and propulsion systems. There's a lot of intermediate steps between what we have today and that all-electric aircraft. And there's a lot of things that need to be worked. The inverters, motors, power storage, power extraction. As we heard, is the ability to pull that power off, to efficiently convert it and store it or use it for electrical demand. For the single-aisle aircraft, really the glue that enables the thermal benefits, EAP really is the glue that enables the thermal benefits. In the turbofan, there's aero benefits to getting lift to drag ratio, propulsive benefits with multiple propulsors running off the water, multiple cores in a distributed fashion. So there's a whole bunch of enablers that can be worked there. The small planes we know we could get a range of 100 to 200 miles out of an all battery for a small plane that's not very efficient. But between what we have now and an all electric aircraft, there are between those two extremes, there are the hybrid aircraft that we're working on hybrid technologies to enable some of these things. So let me go to the next chart. Advance this. So, how do we do this? So Glenn has numerous facilities to support the design and testing of electrified airplanes and components, down to small component levels to full-scale powertrains that are lightweight, safe, reliable, and fault-tolerant. I think Jimmy mentioned that as well. There's a lot of power systems and motors and inverter work that's been done out there. Not a lot that it would meet the kind of fault tolerance and reliability that we need in the aerospace industry, and certainly not lightweight. So there's a lot of work that's being done in many of the test cells, and we've repurposed many of the test cells at Glenn to support the research staff that are working these in conjunction with our industry partners to address any challenges and knock down technical barriers to make this a reality. And again, down at the bottom here, you can see that there's it's not only the architecture, but there's an awful lot of work that doesn't get as much attention, but the enabling work in terms of the components, making them lighter, more efficient, working on new materials, insulation and conductors, kinds of things, and certification in aircraft that we never considered in the past. And that's the kind of research that we're doing. And it's for applications, as Bob mentioned, from smaller UAVs to the multi-passenger quadcopters that will be carrying us around in the not too distant future, all the way up to large-scale megawatt-class systems. As you see in the picture there, that is a layout, the electrical layout, and it was for a single-aisle, I think 737 class aircraft, where we can lay out the electrical system, inverters, the motors, and put some of it up at altitude, which is critically important when looking at any kind of arcing and looking at the insulation and how we run these systems. So it's very, very important. And this is all done at NEAT. We've done it with several partners, and we'll continue to do so. NEAT is a facility that is booked for quite some time now. And it's not just NEAT. And if I had more time, I'd see pictures. There's many cells that are looking at supporting urban air mobility and other configurations, and looking at the mid-power kind of range systems as well. So that's all that I had. I will turn it back over to Bob. Thank you.
All right, thanks, Tim. And I think I'm going to turn it over to Jim Wave for questions for the panel.
All right, thanks, thanks, Bob. Getting Frank Preli back in here, just getting him to start his video back up. I just invited him to do that, so hopefully he'll be, there he is. Welcome back, Frank.
Thank you. Nothing like the local cable provider.
Okay, so we do have some questions coming in. First off, Arjun, what kind of lessons came out of the open rotor demonstrator initiative? Could you talk about those a little bit?
Yeah, sure. Very good question. It's a so it's, at this point it's a over 3 decades effort, right? So the open rotor demonstrator, the first one was in 1988. Many key learnings came out of that. One, which has very little to do necessarily with open rotor, but it was our composite blade technology that, you know, proved itself to be mature enough to immediately go into the GE90 engine. And ever since, every new engine basically has used that technology and expanded it further to composite fan cases and whatnot. For the actual open rotor technology itself, we had a counter-rotating fan. And clearly acoustics, noise was the big challenge on that technology. Over the decades, we've kept working on that with various partnerships within the industry and with NASA. And we have significantly improved it. We, you know, looking at single fan open rotors versus a counter rotating one. Our analytical tools of really understanding the flow, the airflow around these fan blades and optimizing the fan blades, not just for performance, but also for acoustics. We've come a very long way in these 3 decades. And I'm excited about the future on it. Let's just leave it at that.
Excellent. That's great. Yeah, the acoustics of a contra-rotatings are always fun, aren't they? And I guess, you know, CFM modeling and computing power, just the leaps there have helped enormously, right?
That's absolutely right.
Yeah, yeah, good. So let's talk about the low boom supersonic for a second. So if low boom models and everything prove out to be working well, how quickly do you think we'll see actual commercial, you know, commercial or business aviation applications of that? And then how big of a factor is propulsion, the propulsion piece in that? You know, we've seen Aeronautics and the others, you know, kind of floating out there trying to get it going, but just how quickly will that all happen once we get this stuff proven?
So I'll obviously, you know, there are a couple of companies out there that are currently looking at getting supersonic aircraft, supersonic commercial aircraft applications fielded in the nearer term, and they'll have their limitations as far as where they can fly, how fast they can fly, and things like that. And I think most people saw within the last couple of months, the FAA even put out a notice of proposed rulemaking to work with some of the noise aspects, particularly in the landing and takeoff arena. But so I see no reason why that won't progress reasonably quickly. But as far as looking at sort of the long term and how you really open up the market with overland flight, we've got a little ways to go. We're planning on beginning flight testing in the next couple of years, and then going out and doing with the low boom flight demonstrator, the X-59, a lot of community testing where we're going to be flying that aircraft over communities, validating that we really understand how the boom is generated off the aircraft, our design techniques to reduce the magnitude of the boom, if you will, to where instead of a boom, it's more like a little bit of a rumble. And then once we have that understanding, also taking data, and this is a really hard thing to go do, which is the psychoacoustic data of how people actually respond to these different boom levels. And putting all that together into a database that now goes off into the ICAO, the CAPE committee, and really dealing with how you might come up with a regulation or a standard for boom, for overland noise that would allow commercial companies to fly. That's not a short button. It's not a short process. But the most important thing is getting that data and getting real data so that we can have that conversation. Now, once you get there, then you start working with some of the other engineering issues and some of the other regulatory issues in terms of landing and takeoff and community noise and working with those. We see that ramping up here as we start to get a real feel for how the boom's going to look. So I don't know if that really is a great answer for the question, because I hate to try to predict those things with any sort of solid timeline. But I think we're going to see an evolution where these companies are going to start flying what they can in the nearer term. But as we start to get a better feel for the overland and we start to get some real data there, we'll see that that market start to expand.
Great. Okay, so another kind of key element in all of this that really hasn't been addressed much is infrastructure. So when we're looking at hybrid electric or pure electric aircraft, especially if we move to that revolutionary phase that Frank was talking about, what has to happen to the infrastructure? We're talking about, fuel charging, airport layout, things like that. So, how much of a factor is that in actually making any kind of a revolutionary leap?
I can take a stab at that. With an all electric, of course, you're going to have to have charging stations wherever you want to fly your small vehicles or personal flying vehicles. But when you get into the hybrid or for the single aisle, you'll be doing this at an airport, and so you will have to have added capacity to charge, and you'll want to do it relatively quickly at gate turnaround. But the other thing we're looking at, of course, is doing a lot of the recharging as the aircraft is descending. So you'll be using the batteries in the beginning of the flight, not so much during cruise, and then it's like regen braking in your car. As you descend, you might have some excess energy from your turbofans that you can then use to do full or partial charging. So when you're on the ground, you may have a lot less work to do on the ground charging station. You'll need to have ground charging station based upon a contingency if you aren't able to come back with fully charged batteries, but we think that the aircraft itself can do most of the heavy lifting.
And Jim, I would just add that if you look at the other end of it, what we're looking at relative to advanced air mobility or eVTOLs, as Frank said, those will be much more essentially focused on electric, without, so they'll have to be ground charged. One of the things we're doing within NASA is trying to develop an ecosystem approach to advanced air mobility, where we're bringing all the players that are required to get all the infrastructure, the vehicles, the standards, everything you would need to envision the establishment of an advanced air mobility transportation network. And so you'll need to have, the electric power companies in there. You'll need to have infrastructure, and folks that actually do the, build out infrastructure like vertiports and so forth, integrated into buildings and that kind of thing. So far we've been pretty, as we've started to do this, we've held a series of workshops. We've been pretty successful in getting the attention of that community. And of course, there's a big promising market. And so whenever there's a big promising market, you can get, folks' attention. And so it looks like there's willingness to make those kinds of investments. Still early days, but there's certainly a lot of interest in the advanced air mobility side of things.
Gotcha, great. Excellent, thank you. We've seen some demonstration flights of smaller general aviation or small commercial aircraft using solely battery power. But that, of course, the batteries take up most, if not all, the payload, the operating payload. What's it going to take? Maybe it's just battery technology to truly make maybe short hop, general aviation, or light commercial feasible solely on electric power.
I'll take a first stab at that, but I think several of our panelists can probably offer a few comments. Obviously advancing the battery technology is going to be key, but it's more than just battery chemistries. Now the chemistries are important. The more energy density we can get, the smaller, the lighter we can make them. But one of the things you find is really about packaging, and we're doing a lot of work looking at how you package the battery so that you get the safety and you prevent things like thermal runaway. But you got to keep it compact. You got to keep it very compact. Got to keep it very lightweight. That's going to be a key part of making that work. Of course, anything you can do in terms of the electrical distribution system and whatnot to make that smaller and lighter is key. But getting that battery packaging, and there's a lot of research going on both inside of NASA and also out in industry addressing that. Our X-57 is one vehicle that's looking at various ways to do it. We've seen a lot of innovation in terms of how we're packaging the battery that's going into that aircraft. But we're also seeing it as we're working with companies on eVTOL. And like I say, any of the other panelists could probably provide some comments on the innovation and the work they're seeing in terms of that packaging, as well as the work that's going on in battery technology.
Yeah, I'll add to that. It's a good summary. I think it's important. So the high power density storage, electrical in batteries, currently it is way off being able to compete with jet fuel, and the amount of energy you can store that in the volume and mass currently done in aircraft. I think it's important to realize though that, that maturation of the actual battery technologies doesn't have to and doesn't slow down the actual hybrid engine maturation, right? The electric motor generator on a hybrid engine does more than just providing power that you want to store somewhere to use at a later date, at a later time in the mission. It can also provide efficiencies to the overall propulsion system by sharing loads between the different spools. And you can optimize your engine completely different in core sizing when you start tapping into that. So there's one example. Another example is today we have many gear systems on the engine, accessory gearbox to drive all the accessories. When you go to more electric flight, right, and you can replace all that with just the power extraction because you have that capability built within the engine. There's a massive amount of weight that you can take out of the engine that way. So even if batteries aren't mature today to really replace existing routes with full electric flight, the hybrid and electric motor and generator maturation is continuing because it's not depending on that battery technology to be there. Eventually it will be there, and the electric motor capabilities will just have matured and transformed and be ready to do more and more, as that battery technology develops.
Where does fuel cells fit in that equation?
Actually, worked on fuel cells for 10 years of my career, and what I would say is, at the state of the technology today, which is far, far advanced over where it was 20 or 30 years ago, you could consider fuel cell maybe in terms of an APU type application or a continuous power output application during a flight. But if you look at the amount of power you need, the fuel cells would just simply be too big to do anything more than what I just described on a single aisle or a wide body today. And so I think fuel cells have a long way to go on the ground and in cars before they're really going to be able to take over any kind of propulsive duties on an aircraft.
If I can jump in real quick, and I wanted to pull on what Jimmy was talking about with the batteries, and there's an awful lot of battery work that's been done. at Glenn. It's been national experts working batteries and working the size and packaging, and is very right about how you package it in order to have it operate safely. So if you have a failure, that it's contained, it doesn't jump from cell to cell. And what to Bob's comment about developing an ecosystem, it's the same kind of thing with in the battery technology and many of the technologies. Glenn has had numerous battery workshops that have been put together and are working closely with DOE on some of their technologies to try and mature some of these things.
That's actually, Bob, if I can, I had a good question based on what you guys were just talking about. Tech transfer. So, what are you seeing that might be going on, in the defense industry, that might be able to be transferable to commercial or private, propulsion technology advancements, like the F-22 has Super Cruise, that kind of thing. And additionally, though, what about commercial sector hybrid technologies or auto racing? You see Le Mans, you've got some incredibly sophisticated hybrid models on some of their cars, Audi and Porsche. Are you looking at any of that for the aviation sector? Don't all answer at once.
I'll jump in. So the sector that we are looking at is much higher power, higher voltage than the systems in say the automobiles and whatnot. So there are certain things there that are interesting, and we're building on that. But I think at this point we're way beyond. In the lessons that we're learning on how do you control and manage the high density, high power, high voltage at altitude, where the laws of physics are different than, in Le Mans at sea level.
Hey, Arjun, speaking of that, so maybe some of the panelists can talk a little bit about how do we manage those very high power, and especially those very high voltages at altitude, where you've got arcing, corona, all those kinds of things that come in and are serious issues that need to be managed.
So it's a lot of lessons around the insulation and the temperature control, especially within the motor generator itself.
Do we have the materials?
Yeah, we have it working. I think there are material improvements. I think it will set up a whole new science and maturation path for the future, especially within the controller, the silicon carbide components. There are a lot of learnings there that we continue to build on.
So, in all that, to me, it leads to the serious challenges around how do we certify these systems, right? So these are very different systems than we've been traditionally certifying, where we've got good rules, standards, means of compliance, test procedures, all that kind of thing. So what do the panelists see as the gaps we have there to address to be able to confidently certify a hybrid electric system?
I think we'd have to take lessons from the past. We have certified a lot of electrical components for aircraft use, namely on the 787, which is very high, uses a very high amount of electricity. Now we're talking about going to the next level, but I think one of the key challenges is 33 versus 50 in terms of we certify aircraft things under one set of rules and propulsion under the other, and these electrical components, which one do they fit in? So I think first thing we have to do is decide what will be the certification pathway. But then, you know, we have tried and true methods of testing, whether it's a mechanical component or an electrical component for aviation use. And I think we pull those out, and we may have to add some things to that, but these are processes that have worked well in the past, and I think we extrapolate them and enhance them to work well in the future.
Okay. So I think we're just about out of time. Let me just ask you, you know, 30 seconds out of each of you. So what do you see as, what's the biggest challenge you see out there heading into this new future? We start with Jimmy. We'll go down the panel in order.
I would say probably the biggest challenge is the one thing that we probably spent the least time talking about, and I think that's one of the reasons it's a big challenge, which is the supply chain and the associated workforce. It's a little bit different from our traditional supply chain, a little bit different from our traditional workforce, and making sure that they're able to meet the aerospace quality standards, the reliability that we need to get the safety that we need for aviation applications. I think that's going to be a challenge.
Thanks, Jimmy. Arjun?
I think it's, you know, to get to the required efficiencies that we need to get to, the integration between the propulsion system and the aircraft itself is getting tighter and tighter and more unique. Frank touched on it from a certification perspective. It's going to get so blended. That's going to be a whole new level of working together between the engine OEMs and the airframers, so making sure we get the most optimum system.
Frank?
I would say the persistence. I think history shows us that even for very challenging technical problems, if we stick to it and keep on course, we get to the goal we're looking for. So, but we need to do the necessary research, do the necessary technology development, keep moving, and I think we'll get there.
And Tim?
Thanks, Bob. So Jimmy took my first one, being down on the ground here, you know, the workforce, finding the right workforce. You know, we hire electrical engineers, we can hire aerospace engineers, and now we're trying to marry them and knock down some of the challenges. I think facilities are another thing that keeps me up at night, making sure that we have the facilities up to snuff. But with the right facilities, with the right people on board, I have no doubt that we will knock down these technical challenges and get to where we need to be. I don't think anybody expected us to be where we are today 10 years ago.
Great. Well, thanks to all the panelists. I think we're wrapped up.